So first of all, it's great to be here today in sunny London. So that was unexpected. All right, so I'll talk a bit about this Parallelproj library or project. So what is Parallelproj? It's basically it's a small project that implements projectors that are useful mostly for pet reconstruction, right? So what is being done is I implemented basically the 3D Joseph projector, which is a way to compute line integrals. And obviously we have the forward projector and also the adjoint version of that, which we usually call the back projector. And the backend basically has a CUDA implementation of it and also a C implementation that uses OpenMP, such that if you don't have a CUDA machine, you can also run it on a non-CUDA machine, right? And we have dedicated version for non-time of flight and also time of flight projectors, which is interesting for battery construction. And we have dedicated versions that deals with sinogram data and also with list mode data, because if you have time of flight data, then you can do stuff more efficiently in list mode, right? And one thing that I want to highlight is that so we don't only have the backend that is basically C and CUDA, right? We also have a nice, clean Python interface to it. And that interface is what's called Python Array API compatible, but I'll talk about that in a second. And so if you look at what's being done, so this is just what we do is we calculate line integrals or time of flight weighted line integrals, okay? And one highlight is that everything is on Conda Forge. So if you want to install it, basically it's a one-liner, assuming that you have Conda installed. So it's very easy to install. So you don't need to compile it yourself, right? So which sometimes can be a bit messy if you have to match CUDA versions and all that stuff, right? But this is actually handled by Conda and well, all the smart guys from Conda Forge. Okay. So if you go to the website, which is on Read the Docs, so if you Google Parallelproj, you quickly find the Read the Docs page. You can find actually many minimal examples that I set up. And what is usually common to all the examples is that, so the first lines always look like this, right? So what the user can do is the user can actually choose and what I call basically a Python array backend. So you can say, I want to use NumPy as my Python array backend. So that would mean my image is a NumPy array, my data is a NumPy array, and the projector basically projects a NumPy array into another NumPy array, right? But you could also say, well, I have a CUDA GPU and my GPU is big enough, right? So I can fit all my images and my data onto my CUDA GPU. So instead of using NumPy, I say, I want to use QPy, which is basically a CUDA implementation of NumPy, which means that all your data and all your images and data stay on a GPU, and then basically the projection is executed immediately on the GPU, which means a just-in-time compiled version of CUDA kernel is executed on your GPU. I'll show it in a second. And what you can also do is you can run it directly with torch tensors, because there's a nice feature that basically QPy and PyTorch, they're very compatible. So you can say, well, if I want to use torch as my array backend, you can do that as well. I'll have an example on it, right? So basically, if you go through the examples, you will always see that. So as a user, I choose my backend. So I usually call it XP. So it could be NumPy, QPy, or torch, right? So then you can create images or data, right? Then you can forward or back project your data, right? But keep in mind, so if you see XP here, right, it could be NumPy, QPy, or PyTorch tensors. Yeah, right? So that should all work. And then if you want to write a simple iterative update, for example, like an EM type update, right? So you would write it like this. You say, okay, I have a forward model that forward projects something. I have an adjoint step, and I do some, element-wise array operations, right? But this is all very generic, and that works for NumPy, QPy, or torch tensors. So if you go to the website, you see I have implemented many minimal examples. Some are related to setting up scanner geometries, but it's probably not too important. But I also have set up an example that shows you how to build basically a PyTorch network layer that uses the Parallelproj projectors. So this, you might say, well, this should be trivial because I know how to project and back project torch tensors. No, but it's actually a bit of overhead that you have to do is, so you have to read the PyTorch documentation, or I did it for you and Imrush did it, right? So you have to create what's called a torch function, which is compatible to PyTorch's autograd magic, right? So Again, this is not rocket science. You just have to basically stick to the PyTorch conventions. And that example shows you how to do that, right? And what I actually did is I created an example that implements a linear single channel operator. So that could be a Parallelproj projector, but it could be also any other, in principle, linear operator. So Gaussian convolution or resampling or whatever. And so what Imraj already mentioned is a crucial thing that you should always do is, so if you implement those layers, you have to basically implement the forward path and the backward path. So this is not the forward projection and the back projection. It's basically the forward path and the Jacobian vector transpose product. That makes sure that basically autograd uses your function correctly. And then what I always do is basically I show you how to run those grad checks that numerically verify whether those projections and back projections through the network work correctly, such that the gradients are calculated correctly. Okay. So then a few words on the Python array API standards. So what is that? If you have not heard about it, so this is so a few Python people came together a few years ago and they said, well, it's a pity we have now many different frameworks like NumPy, QPy, PyTorch, TensorFlow, whatever, right? They all use some kind of arrays, right? So NumPy arrays, QPy GPU arrays, Torch tensors, they're all arrays in the end. And they said what we should do is we should try to make sure that all the functions or classes that operate on these arrays, they are basically exchangeable. Right? So they show a motivating example here. So let's say your task is you have a 1D array called X, right? And you want to apply a simple signal processing filter called the Welsh filter. Not sure what that does, right? But it doesn't matter. So if X is a torch tensor or a QPy array, basically what you have to write is this complicated code. So you first have to transform your QPy array into a NumPy array, and then you can call function on it, and then you can basically transfer it back into a QPy array and so on, right? And for torch actually it looks a bit different, right? So that means if you wanted to support all those array backends, your code will be very messy, right? Because depending on what backend you're using, you have to write different code. So the aim of that Python array API project is, well, if everything would be implemented well, if the QPy guys and the Torch guys and the NumPy guys would agree on some standards, actually it should be able to write the code shown here in the bottom line, right? So actually, I don't care if X is NumPy, QPy, or Torch, right? So basically what I want is that this is a 1D array, execute that filter. Right? So the aim of the project is that hopefully sooner or later, right, most of the array frameworks will stick to a few standards such that this is possible. And they explicitly mention on their website, so projects that are actively being considered for the standard is NumPy, TensorFlow, PyTorch, and so on, JAX, BASP, QPy. Right? So the NumPy guys, they have implemented a special version of NumPy that strictly sticks to that standard, which is called the NumPy strict version. So what you have to realize is that standard only implements a subset of the functions. So it doesn't implement all the NumPy functions, but it implements the most important ones, such as you can create arrays, you can index arrays, you can slice arrays, and all this. And so QPy is also very well supported, and PyTorch as well. Okay. So I told you that Parallelproj is supposed to be Python array API compatible, and I think that is the case, because if you look at all my unit tests, what I usually do is, depending on what machine you're executing all the unit tests on, I make sure that I test them with NumPy, the basically strict version of NumPy, QPy, and Torch, right? So basically, if you have a system that supports all those backends, I can run my unit tests on all those systems, which gives me some confirmation that I should be Python array API compatible. So if you look at the unit tests, so basically this is just a bit of config on what backends and devices to use, and then all the unit tests are run on all these backends that are always called XP. So this is just for me to make sure that I am Python array API. Okay, so then maybe taking a step back, I already told you that we support different array backends, and we support CUDA systems and non-CUDA systems. So in general, you can say you can run the Parallelproj project in 3 different modes. So the first thing is, well, depending on your hardware, right, you can run it on CUDA systems and non-CUDA systems. On CUDA systems, you can run it in a way that I call the pure GPU array mode, which means your images and your data they already sit on your GPU, so they're GPU arrays, right? And then basically a projector takes, a GPU array and then executes a JIT-compiled CUDA kernel on that array. So everything stays on the GPU. There's no memory transfer between CPU and GPU. So that's the pure CUDA array mode, which is very fast, but obviously, you have to make sure that your GPU is big enough, right? Then there's also what I call the hybrid mode, so which means the input is usually a NumPy CPU array or a Torch CPU tensor, right? And then basically I'm calling a precompiled library, so the CUDA version of my library that first of all transfers the data to the GPU, then calls or executes the kernels, and then transfers the results back to the CPU, right? So this is the hybrid mode in case your GPU is not big enough for your problem. Okay, so those are the two modes that you can run on CUDA systems. And on top of that, obviously, I told you that I also have a version of the library that is written in C and OpenMP. So if you don't have CUDA, right, you can just, or what is being done is basically a function of that pure C OpenMP libraries. If you have a more detailed look, I picked an easy example. So in this project, there's a simple function, which is a Python function that calculates basically the non-top version of the Joseph line integral, right? So that takes an image as the input and also a bit of coordinates that encode where your lines of response are. And then in the end, basically returns the forward projected values, right? So, and again, that function can digest NumPy arrays, QPy arrays, Torch CUDA tensors, Torch CPU tensors, right? So if you look inside the function, what is actually being done, and in the beginning, I'm checking, well, your input image, is that actually sitting, is it a GPU array, or is it a CUDA array, or is it not a CUDA array? So if it's a CUDA array, then I want to make sure that I don't do the memory transfer. I just basically execute a JIT-compiled QPy kernel, right? And this is what's being done here, right? Okay. If your data is not on a GPU already, what I'm doing is I'm basically calling a precompiled, a function of the precompiled CUDA library, right? And then that function first, takes your CPU arrays, transfers them to the GPU, executes the kernel, and transfers the results back. And so basically, this interface is done in using C types, right? So this is a thing to get precompiled C functions into. And the last mode is, so this is the third mode. If you don't have a CUDA device, right, I'm calling the C compiled version of my device. Right? So I guess part of the workshop is about PyTorch, right? So how do we get PyTorch in here? So there's one nice thing. If you go to the QPy website and read their documentation, they have a section on interoperability, right? And there's a subsection on QPy versus PyTorch. And they say that basically PyTorch and QPy, they're very compatible in terms of CUDA arrays because both support what's called the CUDA array interface, right? So that means if you want to convert a QPy GPU array into a Torch CUDA array, you can do it without any memory copies, right? So this is actually how you do it here. So it's very easy. You can basically use this as array methods, and then yeah, it's very easy to do. So actually, coming back to the example that I showed a second ago, right? So if the data is on, if I want to project an image that is already on the GPU, right? So it's either a QPy CUDA array or a PyTorch CUDA tensor. What I'm doing is, for example, I'm making sure that I convert all the input arrays to QPy CUDA arrays, right? So remember, Xstart could be also a PyTorch CUDA array. So this is very fast and cheap, right? And when I return the result, I make sure that the result is also converted back to a Torch CUDA array if the input was a Torch CUDA array. And then going one level deeper, so basically, I told you that basically the backend is implemented in CUDA or in C, right? So if you look into the project, you have a file that defines all the CUDA kernels. And so I separated them because what I do is, I told you in the pure GPU mode, I'm using CUDA QPy just-in-time compiled CUDA kernels. So I have a separate file that has only the CUDA kernels, and I use QPy to just-in-time compile them, and then I can execute them. And then we have basically the second part that is basically that are the wrapper functions for the CUDA version of the library. So those functions, what they do is they take usually, pointers that live on the host, and then they first do the memory transfer to the GPU, execute the kernel, and then transfer the results back. And the third mode is basically the pure C mode. So this is the C version of the library that uses OpenMP that takes float pointers that live on the host. So there was a lot of talking. If we have 2 minutes left, I would show a quick demo actually, which is, I guess, useful. Yeah. Okay. So let's see if it works. So you should see here my VS Code now, right? So and I have created a minimal example that just does basically a forward projection or a couple of forward projections and back projections. And I want to demonstrate that I can use different array backends. So if you look at the example, the first section is only about choosing your backend. So it can be NumPy, QPy, Torch CUDA, or Torch CPU. And I'm setting up a very simple projector, but the details don't matter. What I'm executing in the end here is a small loop that does a few forward projections and back projections and easy element-wise operations, right? And I'm doing it 5 times. And what I should be able to do is, so I can run that now. I'm on a CUDA system, right? I can run that example using NumPy as my array backend. That means the arrays that I create, so the test image that I'm creating is a NumPy array that lives on the host, so on the CPU, right? And then the projector basically calls the function of the CUDA lib that does the memory transfer, executes the kernel, and transfers the results back. So if I execute that, that should take a couple of seconds. So it's running 5 iterations, so to say, right? And you can see that, so on average, an iteration took 4.74 seconds, right? And the input is a NumPy CPU array, and the output is also NumPy CPU. But I can do the same using, for example, Torch and my CUDA device. So now all the data that is being created is a Torch array that lives on my GPU already, right? And that means, so my image is a Torch CUDA array. My forward projection is also a Torch CUDA array, right? And if you see now, well, an iteration is now much faster. It only takes 0.2 seconds. So it's roughly 4 times faster. It's because I don't have to do all the memory transfers between hosts. Right? And obviously, you can also run it, for example, using QPy, if QPy is your preferred backend. So that should result in very similar times. Yeah, roughly the same. That's it. I'm very happy to talk with you. Yeah. And maybe one thing that I haven't mentioned is, so I think this workshop is about getting PyTorch nicely integrated. So the Python Array API has the potential advantage that who knows what the next deep learning framework will be. Could be JAX or whatever, right? So I hope that most of those frameworks will stick to the Python Array API standard, such that once you support that standard, users can choose their favorite. But that, of course, will also take time, right? So they're not there yet.